So, yeah, for chapter 6, section 5, here's our first problem we looked at, this growth rate problem. And give me the growth rate R of t. It says evaluate and interpret this integral. Okay? So, you guys drew a little picture, or on your calculator, a lot of you guys did it, but if I just kind of quickly sketch the graph, looks something like this. I have growth rate. I know that R of 0 is 250. What does that mean? R of 0 is 250. How do you interpret that? Well, what did R of t represent? R of t, it said, is 250 e to the 0.04 t. But what does that represent? This is the growth rate. What are the units? Okay. So in year 0, there's growth. This town is growing 250 people per year. But in year 3, it was growing even more. I think it was 281 per year, is what we said. So this is the picture, right? But in part A, when you say you're going to evaluate the integral from 0 to 3 of this 250 e to the 0.04 t, what you're doing is you're finding this. And I think you guys all worked it out and got 700, what'd you say?
97.
About 797 if you round. And now, what are the units for this 797? How do I interpret the 797? In that 3-year period, the town grew what? People, right. And this was the point that, in a sense, this is like the total accumulation of that growth. And what I was saying was, what would have happened if it stayed flat? Well, it's growing 250, growing 250, growing 250, it would have been 750. But because it's growing more and more each year, that's why we're up to 797. Okay, now that's part A. This is problem 72, part A. So now we're on 72, part B. And I'm going to throw it back up here so we can read it again, so we try to understand the problem. It says a civil planner estimates, hey, 3,000 more people can fit in the town before we start saying, hey, this town stinks. Now, we already know in 3 years, at the way things are going, we're going to add 797 people. Right? So the question is, how many years will it take for the population to reach the number 3,000? Actually, Brian had a pretty nice idea, I thought. He said, look, it's growing 250 per year. If it stayed like that, how many years would it take to reach 3,000? Well, 250 per year, so in 4 years is 1,000, right? So 12 years. So one guess you could make is 12, but that's on the low end. So maybe instead we say 10 or 11, something like that. All right. Now this group back here, Ben and Steve got it, right? You guys got it? What'd you get for an answer?
9.8.
9.8 years? We can check that. Does someone have a graph on their calculator? Hand me one of these.
I don't have it in the graph.
Who has the graph? Just the growth rate is all I want. All right. So here, Brian had graphed from year 0 to 3. That same picture I just drew, right? So if we believe Ben and Steve, we can say, look, second, calculate. Let's compute the integral, because this gives you the total accumulation. So again, choice 7. Lower limit 0. Upper limit, you guys are saying 9.8, huh? All right, let me calculate it. Oh, yeah. $29.99. So what are we going to say? Basically, in that 10th year is when we're going to be in trouble. We're going to be over 3,000 at the rate things are going. Now, how'd you get it, though? That we just did it kind of a guess and check, right? We said, well, it's lower than 12. Let me check. And 10 seemed to work. But they did some pretty interesting mathematics, which I'd also like to show you guys. So we'll take a quick peek. Let me highlight a little bit what's going on here. You guys see this calculation? That's part A, right? And in part A, they computed the 796 just like you did. Okay? So now in part B, they said, well, this answer that we got, 6250 e to the 0.04t, we didn't do plus c in part A. What did we do? We did from 0 to what? 0 to 3, yeah. 0 to 3, because it was the first 3 years. Here, I want to show this. Let me show you maybe a different way to approach it than even Steve did. Okay? Okay. So the idea is we're going to integrate from 0 to question mark. We're going to integrate that 250 e to the 0.04t, and we want this to equal 3,000. But we don't know what that question mark is, right? That's the thing I don't know. You guys with me? Now, we want this. So what we want, now when you integrate this, this is what I just showed you guys on Steve's paper. He had 6250 e to the 0.04t, and what we usually plug in is 0 and question mark with a line here, right? We want this to equal 3,000. Now what's this bar mean? What's it mean you should do? Plug in 0 and plug in question mark, right? So what we get is 6250, let me slide this up so we could see, e to the 0.04 question mark minus 6250 e to the 0 equals 3,000. You guys, what's e to the 0? You see it? Brian, you see what to do now? That's 6250, right? So what we get now is we get 6250 e to the 0.04 question mark is equal to, and this is 1. So if you add 6250, you get 9250, because we started at 3,000. And the first time they did this, they missed that. Oh, we're starting at 3,000. But now, right? Or we're starting at 6250. So now, oh, how do you solve for question mark here? Well, this is algebra at this point. You want to get the exponential by itself. So what would I do to both sides? I guess I would divide, right? Let's take 9250 and divide by 6250. Oh, that's right my way. There we go. Okay, I'm going to do 9250 divided by 6250. I got 1.48. Ben, is that what you guys got? Yep. Okay. So then I get, how do you get to the question mark here? What do you want to do to both sides to get rid of that e? How do you undo it? You take the natural log of both sides. Taking the natural log of the e makes that go away because they're inverses. Do you guys remember that? So 0.04 times question mark is the natural log of 1.48. Okay? And then the question mark would be the natural log of 1.48 divided by 0.04. So let me type that in and see what the question mark is. So if I take the natural log, where'd that go? Here we go, of 1.48, close parentheses, and then divide by my 0.04, I really do get 9.8, just like they got. Guys follow? So again, in 10 years, this town's going to be no good anymore. That's what we're saying. So here's 74. Mobile homes in the Midwest. Oh yeah, I used to drive to college. We would pass the largest seller of mobile homes in the nation.
Oh, yeah.
You know where?
Yeah, that's in Indiana.
In Indiana, on I-80, I-90, right by where the turnpike hits the other interstate. And yeah, so anyways, just like the housing bubble burst, it says, according to our book, that mobile homes stopped selling in the early 2000s also. So that's why this is a rate of change, and notice it's negative. Mobile homes are, the rate of change was going down from the year 2001 to 2011. Okay? Now, if we're going to understand this problem, I think we should graph this function. So I'm going to go ahead and do that. So I'm going to go hit the y equals screen. Oh yeah, we did the bell curve last time. Let's do negative 19.2 divided by x. And now I need to change my window for sure. Let's go from, well, I'm going to go from 1 to 11, I guess. 1 to 11. Now, what about the y values? Well, if you plug in a 1, you'd be at negative 19, right? So how about I go from, like, I don't know, negative 20 up to y max. Well, see, what do you know about this kind of a function? When you put in a really big value of x, what's the limit as x goes to infinity? Well, 0, right. So I put 1. All right, I'll just do that. And then I'll put a mark every 10. I meant to put 0. Just slipped. But anyways, here's your graph, right? It's getting closer and closer to the x-axis. So what is this? This is the rate of growth, but each and every one of these values is negative, right? So like if I hit second, calculate the value at negative 1, I'm doing part A right now. Oh, invalid. Oh, because it's not negative 1. They want f of 1. That. Negative 19.2. See, here's the problem. Let's continue up here. Part A. It says evaluate f of 1 and interpret. Well, we just did. F of 1 is negative 19.2. Okay. So how do I interpret that? So let's see. F of 1 is negative 19.2, and I would say that this means in 2001, because the x is number of years, it says f of x is the rate of change in the number of mobile homes manufactured in thousands per year. So in 2001, there was a loss of 19,200 mobile homes, right? So maybe I'll say the number of mobile homes manufactured in the Midwest was decreasing by 19,200 per year. Wow. Talk about huge slashes. 2001, I hate to be that business, over in Goshen, Indiana. Now, it's still, over the next 10 years, continued to be negative, but not nearly as negative, right? That's what we're saying, not nearly as negative. So now, part B. Integrate to determine the total decline in Midwestern mobile home manufacturing from 2005 to 2010, right? We talked about total accumulation. Well, here's an example where what we're going to do is we're going to integrate from 5 to 10, 2000, oh no, not 5 to 10, because we started in 2001. Wait a minute, let me think. Yeah, 5 to 10. This is 2001, that's 2005, that's 2010. So if we integrate, again, my function, negative 19.2 over x dx, I'll get the answer. And some of you guys were asking me, how do you integrate this? If you pull the negative 19.2 out, you just have 1 over x dx, or some people wrote it as x to the negative 1. So you get this very special integral. How do you integrate this thing? It's the natural log of the absolute value of x. So now what you have is you have negative 19.2 times the natural log of 10 minus the natural log of 5. If you plug those numbers in for x, this is what it looks like. So let me go ahead and try to type that in and then interpret. So let's see. I have negative 19.2 times, open parentheses, natural log of 10 minus, oh wait, make sure I close parentheses here. Do you understand now, Laura?
Yeah.
Good.
We used to put the negative 19.
Oh, okay. So that constant I just kind of brought out front. And then so I'm getting negative 13.3 okay, and so what's that mean? You guys getting the same thing I'm getting? Yeah. So then let's interpret it. It says, oh, it's the total decline in Midwest mobile home manufacturing. So that means over those 5 years, we lost 13,300 mobile homes, right? That's the total decline. Now, not as bad as 2001, right? But still bad for that business. So you can measure total declines also. Okay. Any questions so far? 76. Okay, what's going on here? Part A, evaluate f of 3 and interpret. I think the first thing I'm going to do for 76, before I even write anything down, is I'm going to throw it in the calculator here. It says x is the number of years since 2000. So again, we're talking that first decade of the millennia. F of x is the rate of change in the amount of fish caught in tons per year. All right. So are we catching more fish or less fish as this decade goes by? Well, it's interesting because it's e to a negative exponent, but then there's a negative number. Let's see what it looks like when we graph it. Okay, so y equals negative 6624.42 times e to the, right here, negative, is it 0.22? X, close parentheses. Okay, let me check my window again. I'm going to go from 0 to 10. Now what about the y values? Well, if I plug a 0 in for x, where am I going to be? Negative 6,000, right? So why don't I go from negative 10,000 to what? Well, see, I don't care what you plug in for x, you're always going to be negative. So why don't I go y max is 0, and I'll put a mark every 1,000, just see what happens. Okay, let's look at this graph. All right. It says evaluate f of 3 and interpret. That's pretty easy. Second, calculate the value 3. Negative 3423.84. So how do we interpret that? Well, this is 6.5, number 76. Part A, f of 3 is negative 3423.84. And to interpret it, it's the rate of change in the amount of fish caught in tons per year. So I would say in 2003, the amount of fish caught in the Atlantic was decreasing at a rate of, I'll say approximately 3,400, and it's tons per year. So there's part A. Now part B is going to be about the integral. Part B says, let's integrate from 3 to 5, f of x dx, and interpret. Now I know you could do this, right? If you had to integrate it, there'd be a u substitution. I can show you that if you want. But I think for the sake of time, I'm just going to let the calculator do the work and then interpret it. So let's see. Unless you want to see the u sub. You let me know. But I'm going to calculate the value from 3 to 5. And this says negative 5,539. Okay? And what does that mean? Well, during the 2-year period, 2003 to 2005, what do I say here? So again, it's similar to the problem we just did. What's the difference between Part A and Part B? This is trying to hammer something home. Part A says the rate was about 3,400 tons per year. We're losing about 3,400 tons per year. Now, what if it stayed at that rate? How many tons would we lose during the 2-year period? 6,400. That's not what we got. The actual loss in fish caught was approximately 5,500 tons. Now why? Why was it 5,500 tons? Well, because what happened was, remember right here, this is the rate of 3,400. But by the time you got to 2005, we weren't losing so many fish anymore. I didn't check this, but what is the rate? Let me calculate the value for 2005. Yeah, we were only losing 2,200 as opposed to 3,400. See that? By the way, what is 3,400 and 2,200? It's about 5,600. That's interesting. Okay, so yeah, we were losing a lot. Now we're not losing as much. And by the way, they tell you in this problem, why are we losing all these fish? It says because in the 50s and 60s, the fish, more and more people started fishing faster than the fish could keep up, basically. Okay? And this is just the Norwegians. It's amazing, these numbers, you know? Tons of fish. So, anyways, I think that's a pretty nice example to show the difference between a rate and an accumulation. Integrating a rate function gives you a total accumulation. Okay. So we have two things to talk about today. One's called the average value of a function, and then the definite integral, what it means to finance. Although already, based on what you saw today, you could probably tell me what the definite integral is going to tell you in finance, right? Maybe total accumulation of wealth. Okay. If you know the growth rate of your wealth, then you can get the total accumulation, right? So part B is kind of answering. But what do I mean by an average value of a function? Well, I have an exercise for you to kind of get you started. Could you guys please draw a picture of the area represented by, well, I guess the only way we can do this is if you make up a function f of x. All right, so try it. Draw a little axis and draw some continuous function from, well, here's what I'm going to do. I'll show you. I'll show you my picture. Okay, so let me just go here, and this is going to be my section 7.1 notes. And so here's A, and here's B. And what I want you to do is draw some function. I don't care what, your favorite function. How about that? Right. For me, here's f of A, here's f of B. Fine. You know, maybe it keeps going, I don't know. But when I say draw a picture of this, what I hope you're doing is you're, well, drawing this area. For whatever your function looks like, right? Your function may look a little different. Because we're pretty good with that, right? At this point? That was kind of one of the main points of Chapter 6. So now Chapter 7 says, well, here's a question. Thank you. Can you draw a rectangle with the same area? And here's what I mean by that. How do you find the area of a rectangle? Length times width. Now, I'm going to do this. I'm going to tell you that I'm going to draw a rectangle, and I'm going to let this be the length. My width is going to be the height. I'm just going to draw one rectangle. So it's going to go at least this high, right? But that's not the right answer. That would be too low. I want my rectangle to have the same area as the green. And this, of course, is too high, right? But can I draw a rectangle that has the same area as the green if I were very careful? Well, I guess so, right? I mean, you'd have to make the height somewhere in between. I'm going to guess like right around there. What do you think? Does that rectangle, bordered here, 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 and maybe here, does that rectangle have the same area as the green? No? Why not? Okay. Well, that's the thing. We don't know if they're equal, right? I need this piece to equal that piece, right? Are they equal? We don't know. Maybe if I slide it up a little more, would they be equal? Is there a place somewhere I can put it where they would be equal? Yeah, probably. Because if you put it up all the way, then the white's too big. If you put it down too far, the green's too big. But there has to be some place where they're equal. Kind of a midpoint. Well, here's the thing. Whatever it is, that place, that's what I'm going to call the average value of the function. You might say, why is that? Well, it's like this. Normally, how do you find an average? That's something I've never had to explain to a math class. They all know what their average is. If I say, what's your test average, and you have 4 tests, what do? Add them up and divide by 4. So here, what I'm trying to come up with today is the average value of a function which might be f of x, right? Now, f of x, where's that on the picture? That's this thing, right? This is my function f of x. So when I say average value of f of x on the open interval or closed interval a, b, what I'm saying is, hey, of all the different values that it takes, what's the average? See, I don't know if these are actual lines or numbers. 1, 2, 3, 4. Maybe this is 4.5, and down here is 2.5, right? Or something like that. Well, you could add 4.5 and 2.5 and divide by 2. That might be what Brian was talking about a midpoint. But that's not necessarily going to be the right height. See, the difficulty is when you guys are determining your test average, you know you divide by 4 because there's 4 tests. The reason it's hard to divide by any particular number is because there's really infinitely many x values in here. You see them? So what do you divide by? I don't know. But if you go back to the slide for a second, maybe this will make sense. We're going to take the average value of the function to be this. 1 over b minus a times this integral. The integral from a to b f of x dx. Why is that? Well, because I know that the integral is equal to the width of the rectangle times the average value of the function. And by the way, what's the width of this rectangle? Do you guys know how long this thing is? It's whatever b minus a is. Yeah. If we're starting at 1 and going to 5, then it would have a length of 4. The width is b minus a. Again, times the average value. Well then, if you want to know what the average value of f of x is, the average value of f of x, you just divide both sides by b minus a, And this is exactly what you get. So here's another nice application of integrals. You can get an average not just for your test average, which only has 4 tests, but you could have a continuous function. It's like this, guys. Hey, if I asked you, what's the average temperature today? How do you do that? Are you going to take 24 different temperatures, one for each hour, and divide by 24? You could. But what that is, that's kind of like dividing AB into 24 little tiny subintervals, right? That's not doing it with calculus. When we do it with calculus, we take the antiderivative, the limit. And that's what's really done. So I think this is really kind of cool to understand. Because people talk about the average temperature places all the time. But it's not that we're dividing by a certain number of tests, it's that we're actually computing it with the fundamental theorem of calculus. You can approximate it with these rectangles. So then I want to give you some examples so we can see how this works. Oh, here we go. Is that good, current world population? I made this slide 5 years ago. Do you guys know what the population of the world is now? Is this 7 billion? 8? Hey, we need Google. We don't need to read. We don't need to see me do that. But yeah, we're going to say, what is the world's population? What will be the average world population during the next 20 years? Right now, it's 7 billion, we're saying. Okay, we want to compute the average population. By the way. All right, let's go back to our program here. We want to compute the average world population during the next 20 years. So, that's not what I need. I need this. I need my average value. So here I go. Average world population over the next 20 years. So let's see. Well, it's going to be 1 over. Now, what should I use for B and A here? Okay. So in other words, X, when we do that, X is the number of years past the year 2015, right? And F of X is going to be my population. Okay. So then we're going to integrate from 0 to 20. Ooh, what do we integrate? Let's go back to the slide. What's it say? It's growing exponentially at a 2% growth rate. So how do I do that? Well, here's an exponential function, right? If we say a 2% growth rate, is that what I want? E to the 0.02x? Let's try that, huh? But there's an issue here. I know there's something here missing, guys. Let me fix it. We need that 7 billion, right? So let's say 7 times 10 to the 9th, then times e to the 0.02x dx. So let's do it that way. Okay. So moving on, let's try to compute this. So I have 7 times 10 to the 9th over 20. That's the fraction that is out front. and I'm going to integrate from 0 to 20. Now I want to do e to the 0.02x dx, right? So let's go through the actual substitution we would make, because what we're going to eventually do is we're going to write e to the u here. Now for me to do that, let's go through those steps. What does u equal? 0.02x. So what does du equal? 0.02 dx, right? So what does dx equal? Well, dx is du over 0.02. So I need to put du over 0.02 in for dx. That's the Armstrong way of doing it. I mentioned that to you guys. Okay? So now moving on, let's see what I can do. Well, remember what I said to do with this 0.02? Pull that out front. So I have 7 times 10 to the 9th over 20 times 0.02 in the denominator. And now I'm integrating 0 to 20 e to the u du. Okay. And I'm really running out of paper, but I'm trying to squeeze it in, which is probably silly. When you integrate e to the u, guys, what do you get? When you integrate e to the u, you get? Okay, so we'll plug in e to the, and u was 0.02x. And then we just have to plug in 0 and 20, and then we have it. So I'm really running out of room here, so I'm going to come over here to finish it up. I have 7 times 10 to the 9th over 20 times 0.02. I'm finishing it up over here on the side. And then I'm going to be subtracting. I'll have e to the 0.02 times 20 minus e, well, to the 0. That's the answer. That's the average value of the function. Let's see if that makes sense. Time to calculate. All right. Turn it on. Go to the home screen. I have 7 times 10 caret 9. There's my 7 billion divided by 20 times 0.02. Oh, that's huge. Exponential notation at this point. And then we take that mess and we multiply by this subtraction. So I need e to the 0.02 times 20, close parentheses, minus, well, e to the 0 is just 1. Enter. Okay. So there's my average value. Let's see if that makes sense. I'm going to need some commas here. 860,693. 2209. Oh, okay. So over the next 20 years, what's the average population going to be? 8 billion? 606. That makes sense, right? We're at 7 billion now. 20 years from now, we'll probably be at 9 or 10 billion, but the average population is going to be 8.6 billion. Okay, see that? Good. Okay, last 5 minutes. I had 2 problems picked out from the book. I think we'll just do 1, and that's going to be it. Oh yeah, the definite integral in finance. This is actually a good thing to talk about. You guys know the formula for compound interest? How many people have heard of an annuity? Okay, so you've all heard of that. You make equal payments into the account at equal time intervals. We do them in finite math here at Lakeland, Math 1890. Okay? They take some effort. And now what we're going to do is we're going to do things easily. We're going to take a rectangle sum and approximate it by an integral. See, that top formula with the summation, that's what I use in finite math. They have to calculate all these payments and what it all adds up to. But how many have heard this formula before? PERT. Because, yeah, how often is interest compounded? Well, it might be quarterly, might be monthly. But even if you did it daily or every second, you don't get a whole lot more money than you would monthly. You get a little bit. You get a lot more than if you don't do compounding. You go from compound, but it turns out that in the limit is E. And so this is a really nice formula if you have to do calculations. Just pretend it's continuous interest. PERT. And actually, there are some banks that every once in a while will actually offer continuous interest. All right. This is problem 54 from your book. Actually, in problem 54 in your book, you're saving for your new child. You want them to have money when they go to college. So you say, you know what? I'm going to save $100 a month for college. What a great gift, huh? If you could do that for your child. So let's see. $100 a month. Right? And 5% interest. And the question is, how much will be in the account after 18 years? And, you know, that's this A equals PERT, right? Oh, but that only works if I know the principal, right? But what I can do is I can get an approximate value. I'll say, well, I'm going to integrate from 0 to 18. Well, no, not 18. Since I'm going monthly, I guess I want whatever 18 times 12 is, right? So I'll get that in a minute. But what I want to do here is I want the average value